My name's Sean Parent. I'm a principal scientist at Adobe. I've just got my little 20-year award there, so I've been there quite some time. These days I'm working on mobile digital imaging products. And let's see, in 2013, so 2 years ago now, I gave a talk called C++ Seasoning at Going Native Conference. How many people saw that talk? Okay, about half. A lot of people asked at the talk, after that talk, told me I should write a book. So I thought, okay, I will use that talk as a starting point and flesh out chapters for a book. And then every time I get invited to give a talk, I will try to say yes and use it as an excuse to write a little more. So this talk comes along pretty far. My working title is Better Code, and each chapter has a goal, right, to try to achieve better code. And they're stated specifically as goals because I think they're things to strive for, not necessarily things that you can always achieve. So not rules, stronger than guidelines, something in between there. Now we're talking about concurrency. And there's common themes that kind of build going along here. One is that keeping code simple is all about managing relationships, right? Code gets hard when things get very entangled. If you can look at a piece of code and reason about it locally, it's much easier to understand it. I'm somebody who believes that understanding the fundamentals is important, all the way down to how transistors work, which I think I gave a talk last year on how transistors work. It's very important to understand that what we are doing is using mathematics to explain the behavior of a physical object, the machine, not trying to go the other way and take some notion of mathematical purity and simulate that on the machine, right? So there's always, when you're programming, contentions between efficiency and safety, and there's just no escaping it, right? And then I always try to code simply, right? And that just means, first thing, try to get my ideas down in the most cleanest, simplest form I can, and then try to iterate and pull in the rest of the items. Now, to set a little context here, I want to show, start here. So this is just the Chrome browser running there. This is a 37.5 megapixel raw image off a Leica S2. There are no plugins in this browser. And we will drop the image there. And that opened up. And these are the controls that you would find in Lightroom, running inside the browser, right? So you can reduce clarity and crank up the vibrance and take the shadows out. Okay, so this is actually the entire rendering engine from Lightroom running inside the browser. Now, a few years ago, I brought the rendering engine from Lightroom up on mobile devices for products like Lightroom Mobile, and I thought, could I do it inside the browser? So my first thought was see if I could use it using Google's Pinnacle technology. How many people know about Pinnacle? Almost nobody. So it's kind of cool. You have a full Clang C++ 14 front end. This is about 5 million lines of code that's compiled here. So you compile that code into what's essentially LLVM bytecodes, although it's a particular subset of LLVM bytecodes that Microsoft's defined. And then the back end of the compiler executes inside the browser when that code is loaded. And you get pretty much native performance out of the code, right? They don't have full SIMD support yet, so I had to turn SIMD off here. But this is lighting up all 8 cores inside my browser. I have full threading support, and it's just running in a heavily sandboxed environment. Okay, so you can actually run native code inside of Chrome without installing plugins, just download it off the web, and it works quite well. This, however, is the Safari browser. And you'll notice, way up in the corner, you probably can't read it. In Chrome, up there it said running Pinnacle. Here it says running JavaScript. Okay, so this is also a raw file. It's one of our test files that I pulled down, and it's off a Sony, I don't know, it's about a 24 megapixel image. And you can see we got the sliders here, so we can adjust this thing. Okay, and we can go up and down. Now in this environment, this is the same engine running. I have the complete engine up here. I'm not connected to the Adobe network, so all I can show is the sliders, but there's that little run test command, so we can actually run the entire test suite for the engine and validate the results out of here. And what you're seeing here in JavaScript, though, is this is compiled with Mozilla's mscriptum compiler, also Clang-based, but it compiles to JavaScript. So this is about 5 million lines of C++ code running inside of JavaScript, inside of a browser. This is the Safari browser, not Firefox. Asm.js is optimized, or mscriptum compiler is optimized to put out the subscript of JavaScript known as asm.js, which Mozilla has been optimizing for. Chrome actually runs it very well. But this is Safari, which isn't heavily tuned for this. And yet it runs quite well. And there's no threading support in this environment. Okay? So there are things that are probably pretty hard to see, especially on this monitor. It's a little too fast there. But when you're sliding the slider, the image actually gets blurrier than it needs to be. And you can see a little pop there. Now, I'm not actually letting up with my finger, right? So it gets blurry. And then right there, you see the little, it gets crisp. Okay, that's because when we're not able to keep up with performance, it does dynamic rendering and it drops the resolution and turns off some stages in the pipeline to try to go faster and keep up. Okay, and this is all happening asynchronously but single-threaded. Okay, well, and the way that's happening is we're just chaining tasks. So we're putting tasks on the main event queue and coming around. So in order to get the engine running here, I had to remove all requirements of threads, okay, from the code base. Okay. So first, some definitions. Concurrency are when tasks start running complete in overlapping time periods. Okay, but parallelism is when two or more tasks execute simultaneously, right? So cores give you parallelism. So why do we want concurrency in our apps? Well, concurrency enables performance through parallelism, and it improves interactivity with the user, right? You don't want to be blocking the user when the user is using your application, right? So my goal in this chapter is no raw synchronization primitives. Okay? What do I mean by raw synchronization primitives? Mutexes, atomics, semaphores, memory fences, condition variables. These are all way too low-level things to be programming with day to day. And yet I see lots of code where developers say, oh, I've got this object, and I'm going to share it with a bunch of threads and stick a mutex on there and bang on it. The reason why you don't want to use these things is you will likely get it wrong. Here is an example of, this was a copy on write implementation. I actually wrote this, so I get to pick on myself here. This shipped into product, and that product had a very slow memory leak, and we had a really hard time hunting it down. Do people see the memory leak? I highlighted every place where my atomic count gets bumped around there. Okay. There. Yeah, so what happens here? So, yeah. So, if the owner count is 1, then we own it, no issue. We can go ahead and assign into this thing. Okay, but if the owner count is not 1, then we need to create a new object, decrement our ref count, and take ownership of the new object. Okay, which seems very reasonable here. But between the time I checked when the owner count was 1 and when I did the decrement, the owner count could have fallen to 1. Okay, in which case my decrement, my count went to 0, but I didn't delete my object. Okay, so there's a race condition between those two instructions. Right? So that is how you have to fix it. Right? If when you decrement, if you hit 0, then delete it. Right? Right? And I've actually had engineers come back and say, well, why do you do that? You know. I knew it was 1 then. Yes. Okay. Performance through parallelism. A lot of people don't know where the performance is in their machine. I think I gave this slide a few years ago here. Had a talk. So how many people have seen this slide? A few. Yep. So that's about how much performance you have in your desktop GPU. Okay. That's the performance you get with the SIMD unit. Okay. And we have no SIMD support yet in C++, at least no direct support. Okay. That's how much you get just lighting up multiple cores. And that little sliver down there is just straight line on the CPU, one thread, no SIMD. Okay? Okay, so if you're not thinking about concurrency, you're leaving 99% of the performance of your machine, literally, on the floor. Okay. Now, getting performance is not that easy. This is a graph of Amdahl's law. Does everybody know what Amdahl's law is? No, a few people? Okay, so the basic idea with Amdahl's law is it says if some percentage of your code needs to be serialized, that ends up putting an upper bound on how fast your code can go, right? If 10% of my code needs to be serialized, I can't do any better than 10x performance increase, okay? Because that keeps adding up. Right? Right? So this is the graph. So every time you need synchronization, every time you need a mutex, every time you block on a mutex, every time you share memory, right? That's bumping you into Amdahl's law. Now, so if you Google Amdahl's law, this is the graph you'll find on Wikipedia, and everybody puts this graph up, and I hate this graph. Okay? Does anybody know why I hate this graph? I think it's very misleading. So it's labeled properly. So down here we have number of processors across the bottom and speed up across the top. It's a logarithmic scale across the bottom. Okay? And it's a linear scale up the top. Right? And this top curve is a 95% of your code is running in parallel curve, which is going to cap you out at a 20x performance increase, somewhere around 4,000 cores. Okay? Nobody has that many cores, at least not in a couple people in this room might. I don't. Okay, most of the stuff that I do runs here. If you wanted to draw the line that started down here and was full parallelism, 100%, no synchronization, so the top right corner of this graph at this scale is pretty close to the moon. Okay? So this is Amdahl's law looking down at the origin on a linear scale. Okay? Each arc off here is 10% synchronization in your code. Okay? And you just can't escape this, right? So if you just have 10% synchronization and you're just looking out here on a 4-core machine, you're only getting a 3x speed up, right? You've already lost 25% of your machine right there. Right? 10%, 4 cores, 25% performance hit. Okay? So, these are the things that kill you, right? Spell slow. And here's the way most people tend to think about threading. They say, oh, I got my object. I want to bang on it with a bunch of threads. So here's how I'm going to do it. I'm going to stick a mutex on there, and I'm going to let them cycle around. Don't do that. That kills you. No stops. Okay. When I'm running on one thread, right? If you know anything about STD futures has .get. I call .get, that's a deadlock. I'm done. I call .wait, that's a deadlock. I'm done. Okay? So, threads and tasks. Threads are an execution environment consisting of a stack, processor state, running in parallel to other threads. Okay? So, these are things the OS provides. We have them in C++11. You can spin them up. Threads, depending on your OS, can actually be quite lightweight to be flipping between them, but they are quite memory intensive to bring up many of them. Okay? They all need their own stack, their own execution environment. Okay? A task is a unit of work, often a function, okay, to be executed on a thread, some small little thing. So frequently we schedule tasks on a thread pool where we create one thread per core on the machine that we have, and then we will just schedule those tasks on the thread pool instead of just spinning up a load of threads. C++ 11 and 14 don't yet have a good thread pool. Okay? So we have threads, we have futures. Futures are very broken. Now, this is our adventure game talk. Where do you guys want to go from here? We can talk about futures, or we can talk about building a task-stealing thread pool system. Anybody? Vote? Okay, we got to do hands. Okay, so how many people for building a task-stealing system? Okay, so how many people want to talk about futures? It's split. I'm going to take you guys on futures. It's pretty close. Okay, so what's the deal here? You've got a task running, okay? You want to get some information out of the task, some object, and you need to hand that over to some other task somehow and keep going, right? Right? And you don't want to be stopping there on that. Okay? So, how can you do it? Okay, well, we can do an async operation, and that returns a future, okay, for in this case, a CPP int is a multi-precision int, so kind of infinite precision int out of Boost library. Okay, so we're going to asynchronously calculate Fibonacci of 1,000,000 and then print it. And that .get there is bad, but that's okay. Okay. But we have to take a little break here. This is my public service announcement. So early on in this conference, somebody also used Fibonacci as an example for doing parallel code. And they said, look, I can calculate Fibonacci of 20, right? And I can fan it out parallel. Fibonacci always gets used as an example for how you do parallel programming. So how many people have seen Fibonacci used as an example for doing parallel programming? Yeah. So how many people know how to calculate Fibonacci efficiently? A few people. Okay, good. So because I've actually seen people who think that the way you calculate Fibonacci is doing recursion. But in fact, Fibonacci is a linear recurrence. Okay? And to calculate a linear recurrence, we can use a power algorithm here. Right? So this is a generic implementation of a power algorithm. It will take a number and, like, if the operation you supply in there is addition, then this gives you multiplication. If you apply multiplication in there, then this gives you what you would think of as raising a number to the power. Okay? So this should really be in the standard library. I'm looking at you there, Marshall.
I put it in the Boost algorithm, so I was just checking to see if it got into 158.
Okay. Okay. So the algorithm here is known as Egyptian multiplication, or the Russian peasant algorithm. And if you want to read all about it, you can look at one of Alex's latest book, From Mathematics to Generic Programming. Okay. Woo. let's back up one. Going back there. Okay, so now to calculate Fibonacci, all we have to do is we create something called a Fibonacci matrix, which here is this matrix right here, 1110. Okay, so we take that matrix and we raise it to a power, and the Fibonacci number just happens to be hang out right in the top left corner of it. So all we need to do is be able to multiply a 2 by 2 matrix, okay, and we need an identity element for a matrix. We pass that into power, and that will calculate the Fibonacci number and return it. And that gets us to this slide. This is the Fibonacci number for 1,000,000. And it's right. Anybody know how I know it's right? You can actually Google Fibonacci number for 1,000,000.
How do you know Google's right?
I know we're the same. Okay, so that's how you calculate Fibonacci. So when I use Fibonacci as an example here, I'm not doing this really, fanning out, doing it massively parallel. I'm just calculating it on another thread. Okay. So, what are futures really? So futures really, we can take a function, okay, and we're splitting off the result for the function. Okay? So we get a token, that's our future, for the result of the function, and we end up with a function that can still take arguments, the same arguments it has, but now it has a void result. So we're just slicing off, separating the result of the function from the rest of the function. And now we can pass that function around someplace and call it. Okay? And when it gets called, magically the answer shows up in our future. And the future can go someplace else. Okay? So, futures allow minimal code transformations to express dependencies. Right? So, futures can also propagate exceptions. Okay, so if I have an exception that gets thrown on a thread, here I just did a throw, runtime error failure, and then when I try to get the value out of my future, it will re-throw that error, even though that error was thrown on another thread. Okay. So, now we're able to do this, okay, but then we do that get, and we stop. Okay, I don't like get, I don't like to stop. Okay, and then the result comes over, and then we can go again. Okay, so C++ 14 futures lack continuations. Okay, how many people here have seen like boost futures, no dot then? Okay, quite a few. They lack joins, win all. Boost futures have a win all. HPX has a win all. They lack split. What do I mean by split? What if I want to take a future and have two continuations going in two different directions? Okay, okay. C++ 14 lacks that. HPX has it with a shared future. So I hear.
14 kind of also has it, which is shared futures.
It has shared futures, but it doesn't have continuations. So, and the shared futures are weird because you still only get once. So you can share them between many things, but well, no, that's not true. No, you get a reference to it. They lack cancellation. Okay, and every time I throw out the term cancellation, people have a heart attack because they think of like killing a thread, which would be a horrible thing to do. What I mean by cancellation is if I let go of my future for that function, that means I no longer care about the result of that function. If that function hasn't started yet, I would like it not to start. Okay? Further, I would like it to release, okay, to give up whatever lambda or function object it's holding on to, which it might itself be holding on to additional futures that it's waiting for something like a win all, and I want that to unravel. Okay, so that's what I mean by cancellation. It's not stopping something that's already started. It's not starting something that hasn't started yet. Okay. There's no progress monitoring except for ready. You can say, is this thing ready? But there's no way to say, like, how far along are you in this calculation? So, and C++ 14 futures don't compose very easily to add these features, right? If you want to add cancellation in the way I described it on top of the existing future mechanism, I think you end up just rewriting futures, which is kind of where I've been. Okay, so we can do this. Let's see. So blocking on STD futures has two problems. We're consuming one thread resource, okay? And if you think about it, even with a thread pool, that's a big problem because it's like as soon as I have a .get in there, I need two threads. If whatever I'm waiting for in my .get has a .get, I need 3 threads, and so on. And so 3 threads, I've got 2 cores on this device, I'm already out of my thread pool. Okay. So any subsequent non-dependent calculations on the task are also blocked. We already talked, we don't have continuations, but GCD does in a form. GCD is Apple's Grand Central Dispatch, also known as libdispatch. It has something called serialized queues and groups that you can use for continuations. PPL has chain tasks. TBB has flow graphs. TS concurrency will have continuations. Boost futures have them now, kind of. HPX has them. So they're coming. Okay, so this is what a continuation looks like. This is with boost continuations. So we can calculate our Fibonacci number, and then we can print it out, do something else. Okay? Now, and you notice I picked a smaller Fibonacci number, so it's just that. The interface here is kind of cumbersome, right? We get a future in the function we're passing and not the actual value. And this is another design point that I kind of disagree with where futures are going, because the reason why they're passing the future there is so that the function there gets a crack at the error, okay? Which means, but nobody ever does that, right? I've seen a bazillion of these and maybe one piece of code that looks at the error. So everybody has to take a future and then call .get on it instead of just getting the value. And that just messes up your code, right? When you get a win all, which is a way to splice things together, you end up with a future of tuples of futures. So, and that can be painful to unwrap, right? So this is what a win all looks like, right? And a win all doesn't block, right? The way a win all works is you have one task that drops in one result into some shared state, decrements a ref count, and then another task drops in another shared state, and then kicks off the next task. Okay? Okay, so when you have a win all, lots of people think, oh, well, a win all, that's going to like block somehow until these things are all there. It's like, no, it will just chain itself on. Okay, so here's what win all looks like. Now, boost futures are kind of a pain in the butt because they're move-only types, right? And I contend that if I've got a future for an int, it should be a regular type like an int, okay? So here you can see I have to move my futures into win all, and then, right, so what I'm doing here is I'm calculating Fibonacci of 1 million and 2 million, and getting the result and multiplying it together. Okay, and you can see how cumbersome that is, right? I really want to just say like x times y in the middle there, right? But I have to get, that first get is to get my tuple, and then out of the, right, because I got a future to a tuple coming in here, so I get the tuple out of the future to the tuple, then I can get my first item, which is a future to my int, and then I can get my int. Okay. So f is a future of tuples of futures. So the result here is that big. I did not print that one because it doesn't work with the keynote. Caused it to crash. Okay. So the other thing you want to do, right, if I can do joins, I want to be able to do splits, right? Right? Now, you could always say, well, I could just have a function that said go do these two things in parallel. But when you're working on an application, the typical scenario here is you're like, well, I'm calculating the next state for my document. And the user hits Command Save. So I want to say, okay, well, when we're done calculating the next state of the document, go and save it. So it's .then save. Okay? And then the user says, do the next operation. And we want to say, oh, okay, well, .then do the next operation. Okay? We don't do the next operation after the save. We do it in parallel with the save. Okay? So this is again with boost futures. And it's like, oh, well, this is very nice. It looks like we can write this. And that's what happens. We get a sig abort, adding the second .then. Okay? And it's because these things are move only, and that first .then consumed my future. Okay? So in Boost, you can come along and say, well, give me something called a shared future. And if I do a shared future, if I do a shared future in Boost, then what will happen is my second .then will overwrite my first .then. In HPX, I guess you get actually two .thens, right? So then I don't crash with a sig abort, but it only executes down one of my branches. Okay, we could patch that. Okay, we could get multiple continuations. We can write a split function here. So, and this I credit to Bartosz. I watched a talk on him on how to do kind of functional composition. So this is like the most, I don't know, non-functional application of category theory I think ever. You'll see why in a moment. So here's what we're going to do. We're going to write a split function so that if we've got a future x, we can split a new future off of x. That gives us y. And then we can add a continuation. Or I'm sorry, we split a new future off of x, and then we can add a continuation off of that. That gives us a new future for y. And that left x intact, and the way it did it was it created a new future and put it in place of the old x, right? So split is actually modifying x there. Okay. So now we can actually do that. And that's what that will print out. Okay. So here we're calculating Fibonacci of 100. And then we're multiplying it by 2 and dividing it by 15 and printing both the results. Okay, so building blocks. Promises with futures. Promises are the sending side of a future in the standard. Okay, and I think promises kind of get in the way. I think the right granularity is you actually want to have your package task in your future. Okay, but right now we have promises. So you can just create a promise like that, and then you set the value on the promise, and the promise shows in your future, and that's the building block for package tasks. The reason why that gets in the way is there's no hook on a promise to know when its associated future goes away, right? So you can't do cancellation from that. Okay, so, but we can use promises with the existing future mechanism to write our split function. So this is what split looks like. Okay, so we've got the future we're splitting x here. The first thing we're going to do is we're going to move that out of a way into a temp. Okay, then we're going to construct a new promise, and we're going to get a future out of that promise and put it into x, where x was. So now x is brand new. Okay, and then, okay, off of our temp, the original x, we're going to add our continuation. Okay? And our continuation is going to hold on to the promise. Okay? And when it gets called, it's going to get the value, and then it's going to set the value on the promise, which is back on the future for x. Okay? And it's going to return it. Okay? Which will be the value returned through this promise. People kind of follow that? So that's how we can split a future. Okay? But we need just a little more, which is we have to handle what if there's an exception in there. Okay, so this is how we can split a future that has an exception. And this will now split the exception and send the exception down both branches. Okay? Okay. So that's how we make split work. Okay, cancellation. When the last future destructs, any associated task that hasn't started should not execute. It becomes a no-op. Okay? And the resources held by that task should be released, which likely contain other futures. So you want to kind of unravel up releasing resources. Since tasks that may hold futures for other tasks, right? Yeah, tasks may hold futures for other tasks, like I said, you just unravel. So right now, if you call std async and you get back a future and you let that future destruct, the system blocks until that future is fulfilled. And that is a horrible, horrible behavior, right? You never want to block on destruction. So, I do not know of a way to get cancellation into the existing futures. I've tried a couple times. Okay, but this is what I want, right? So we can end up with splits and joins with a graph like this. And let's say that we let go of the future in the top right-hand corner there, right? I want that future to go away. It takes with it the task, okay, which that lets go of those two futures, and they go away, and we're left with that execution chain. Okay, so I want my system to just unravel back up. People follow? Question?
So you said that the future will not start if it hasn't started already.
Right, yes.
But can you maybe give some insight why do you think it would be bad to cancel a running future, for example, running task by throwing an exception?
So, well, you need someplace within that task to throw the exception. So you can do it. You can set like a little Boolean variable and say, repeating the question. So what do I think about canceling a task that's already executed, that's already started? You can do it, but you need a way to like set a variable that can be pulled from in that task, or some way to pass information to that task so that it can pull it. I can't from another thread throw an exception, inject it into some other task.
I'm sure you're familiar with Posix thread cancellation, and on some platforms that's actually how it's implemented.
Yes, the comment was he's sure I'm aware of Posix thread cancellation, and that yes, that is somewhat how it's implemented. And Posix thread cancellation does not work particularly well with C++. Right. You're just halting a thread at some point and unraveling it, and you're usually ending up in a bad state. Right. So futures. We could implement them. Okay? So the way futures work is they have shared state between our package task and our future. Right? And so we need a way to take something like this, like a split, and that gets transformed to something like this. And this is to allow cancellation. What I have is every dotted line there is a weak pointer, and every solid line is a regular shared pointer, a strong pointer. Okay? Another inflection point. We could talk about something called property models. How much time do I have left?
50 minutes.
15 minutes?
5-0.
5-0. 50 minutes. Then that's easy. Then we'll talk about building futures. Okay, so let's look at what building a future is. Now this is not a complete future, but I got a link at the end of this where I've got kind of a proof of concept library with futures that support a bunch of features that I'll talk about when we get to the end. We can take a quick look at it. So this was kind of the start of that library, simplified for the slides here. So this is a little thing that I hope ends up in the standard at some point, which is if I've got I can get the result of a type, but I can't get the result of a little signature expression, like something that you would pass to function. So I think the standard result of should just do it and support both, but it doesn't. So basically what I want this is if I say result int of double, it yields int. Okay. So we're going to build package tasks and our futures, and we're going to forget about promises to do this. Okay, so our future is going to hold on to a pointer to the shared state. Okay, and we're going to have a continuation on there. And just for debugging here, I'm going to put a .get on there because it's kind of handy when you're doing stuff in the console and you actually have threads. And then my package task is going to hold on to the weak pointer to something, right? So all arrows going to the right in my diagrams are weak pointers. Everything to the left is a strong pointer. Okay, and the package task is just callable, right? Some callable thing, but it returns void, right? Because we slice the result off into the future. Okay. The next one. There we go. Did that flip? Oh, I can't see the little side marks from here. Okay, so yes, so we walked through that. Okay, so now we need some way to create these things. The normal thing that you would do is you would create a promise and you would get a future out of it. Okay, well the promise, the deal is I want my package tasks to go away if there's no futures referring to them. So I'm not going to like create a package task or create a promise and get a future out of it. I'm just going to create my package task and my future at the same time, right? So I've got this function called package. You pass it a function, it splits that function and returns to you a pair of the package task and the future. Okay, we can make it a friend there so that we can construct. So the only way to get a future is building out of here. Okay, and that's what the implementation of package looks like, right? It's going to make our shared thing, which we haven't defined yet, and then construct both our future and our package task and return them. Okay, so this is what this looks like. I say package int double f, I get back something that's callable as a void double and a future for an int. Okay, so here's how we're going to construct this thing. So from the perspective of the future, we only know about the result, not the entire signature. But from the perspective of the package task, we need to know about the entire signature. Okay, so I just split this with inheritance, okay, to put it in there. So the only virtual thing I'm going to have is just a virtual destructor, so I can clean it up correctly. Right? And if we got rid of get, we could get rid of the condition variable, but we need the condition variable if we're going to have get. So usually in my code, that's just like debug only. Okay, so now our package task, we can say it's a weak pointer to the shared thing. Okay, and that's what it looks like, and we can default construct. Okay. And our shared item, right? This is the way our call operator is going to look. We're going to set in our base class the result of calling the function. And then we're going to zero out our function. Okay. So shared base here. This is what this looks like. Oh, the vector R up there with the comment optional. That's because when I was doing these slides, I was doing it without boost to try to keep it in pure C++ 11. So as a poor man's optional, I said, well, just give me a vector of R that contains 0 or 1 things. So that's a poor man optional. Hence the comment. Okay, so when we set the value, we're going to have to acquire mutex lock, and then we're going to have to push back, set our optional, okay? And then we're going to grab any continuation clauses that we have, okay? We're not going to go execute them inside the lock. We're just going to snatch them out of the lock. Okay. So this is what a .then looks like. Right? Oh, wait. Yeah, let's do that. We got that guy. Here we go. Here's our .then. Okay. So our .then, okay, Okay, we're going to create a package. It's going to hang on to our shared pointer. Okay. And then we're going to call .then going down with that package. Here's the way our then, another lock, somewhat unfortunate, but we have our lock in, and then we can push back our then clause, okay, because we keep a vector of continuations, so we can execute many of them. Okay, but if when somebody calls .then, we have the issue where the value might have already arrived, okay, so we're going to check if it's already arrived, okay, and if it has, then we're just going to call async move, just execute our then clause right there. Okay, so that gives us that. Okay, that's the transformation we just did. Okay, so we can call it like this. Okay, we can write our own little async function, right? And this is just on top of threads. Right? Comment there. Probably want to replace that with a task queue. Okay. So all we have to do is we take our function, we package it up, binding the arguments that get passed into async. Okay. So that package there is a pair. The first item in the pair we send off to a thread. That's our package task. And the second item is our future. We return it. Okay. So now we can do that with two then clauses with no split in there, and we get the right result. Right? Now exercises for you guys. Add support for joins for win all. Broken promises, which I don't have here. A broken promise is when last instance of your package task goes away. Nobody can fulfill the future. So that should throw an exception that's a broken promise that says this function's never going to get called, right? Sorry. Exception marshalling. I didn't do exception marshalling in this, where we can propagate the exceptions through. And then progress reporting, which is a bit of a harder nut. Put it in there. Okay. So I'm going to insert my own inflection point here. We can look at the library a little bit that I've been working on. I can't see that clock. Time?
20 after.
20 after. Oh, good. Okay, so we should have time for both. So let me flip over here. Do people have questions at this point? Question?
I
Yeah.
just wanted to mention, you mentioned that when you were talking about HPX and the sort of two dot thens,
Yeah.
what you said I think was incorrect. So it does in fact work just as you intended, that it'll
With-
have multiple continuations.
With shared pointers
Yeah, with-
in HPX,
Yeah.
not in Boost.
Yeah.
Yes. So yes. Yes. But it doesn't do cancellation.
We have something.
Cancellation?
We have
We
something kind of
discussed it yesterday, but we're not sure if it really works.
Okay.
But it should.
Okay. Interesting. Okay. So this is a little library that I put up on GitHub. This is github.com/stlab, libraries, and then the stlab library is in there. You have to be on the develop branch. I haven't rolled this to master yet, so if you're like, where is it? You got to be on the develop branch of that. And this is just part of the README file, so I can show the code if we want to look at the code, but that's not particularly interesting. So a couple things here. So my package tasks, like I said, are fully regular type, but they, I can pass them around, copy them around, but I can only call my package task one time, right? Because then it propagates its value through and clears itself out. My futures are also regular type, and Eric Niebler said, well, what about move-only types, right? And we tried it, and it didn't work, just at lunchtime. So I fixed it, okay? So here's what happens. You can have a future to a copyable type, okay? And if we look at the signature here, we have like .then, which is overloaded for R value references. So if the future that you have is an R value and nobody else has a copy of your future, then when you call .then on it, we know there's only one instance of that of a continuation on this future, and your argument will be available to you as an R value. So if your continuation takes its argument by value, you can just move it out and you're good to go and no copies happened. Okay? And then we've got similar thing for get try. I don't have a get in here, I just have get try, and get try returns an optional. It's boost optional. Okay, so you either get the thing out if it was ready or not, or it will throw an exception if an exception has been propagated through the system. I also added something called cancel try, which is if you don't want to destruct your future, but you just want to let this thing go, you can call cancel try, and that will return true if it really did cancel the thing. Otherwise, it will return false and your future is still valid. Okay? And then I've got win all and our package function that returns the pair and our async op. Async takes a scheduler, so you have to pass in a scheduler. And if you want to see what a scheduler looks like, here is a little scheduler that just sticks it on a thread and detaches the thread. So that's what std async effectively does. And here is a scheduler that uses Apple's libdispatch and dispatches it off Apple's libdispatch. So you can do that. Now, what I settled on after the conversation with Eric is if you create a future with a type that is not copyable, except for void, okay, then the future that's returned will be a move-only future. And it can only have one continuation on it, and it behaves much the same as STD futures. But if what you pass to it is something that is copyable, then you get the capabilities of doing the splits, okay, and copying your future around all you want. But even if your thing is copyable, if you just use it as an R value, you'll still be able to pass things moving all the way through the chain. Okay? So I put that up there. That's about the state where I am. I've got a bit more work I'd like to do here. What I want to be able to do is optionally, when you pass in a then continuation, since mine get the actual value and not a future, right, which makes it much nicer to call these things. But that doesn't give you a crack at handling the error. So when you attach a continuation, I want to have an optional, another argument there, which is a recover function. And what a recover function looks like is it receives an exception pointer, and it can return a value of type T from your future, or it can rethrow the exception. Okay, so if you want to, you can attach a recover function there, and that gives you a crack at handling the error. So just along whatever branch you're on for that continuation. Okay, I haven't written that though. No, but this is all up on GitHub, so you can play with the code. The code is a bit of a mess because I hacked in support for move-only types over lunch. If you create a future void, which is supported, sometimes you want a future that's scheduled like on your main event loop. So what it actually does is side effects when it executes. You can have a future void, in which case get try returns a bool, and so you can see if it's there, but that's still a fully copyable future. Okay. So that's that. Okay. Now, what if we persisted the graph, right? We've been drawing these graphs, and the deal with kind of futures is that we build these things up we execute them once and we tear them down. Okay, right? The whole thing with futures and package tasks they are a fire once mechanism. And they're not particularly cheap. I mean, if you look at my implementation and you look at the HPX implementation, they're on par. We can do some optimizations in there, right? We can tune it a lot, but they're not particularly cheap. Okay, so what if you persisted the graph, right? Well, if you did, you would have just invented functional reactive programming, right? This is what functional reactive programming is. Okay, you change your operator names. Instead of .then, you get .map. Okay, and what happens with .map is it can be getting a stream of values through it. It gets called repeatedly, and every time it does, it can map that value to some other value. It does a transformation. That's what a .then does. Okay, so that's the basis of functional reactive programming right there. Just don't throw the graph away and keep running numbers through it. So that would give you that. Now, the way you're building these graphs in your code is you're writing code that looks imperative, and behind the scenes what it's doing is it's constructing a dependency graph, okay, which you may or may not be holding on to, and then you're executing through it. Okay? But how do the graphs change during the execution of your program? Right? If you stand back for a minute, your code is static, right? So you've got conditionals in there at runtime, so you can create, sometimes I can create a branch that goes this way, sometimes I can create a branch that goes that way, okay? But you can somewhat think about it as I've got a graph that I'm going to keep appending to with structures that I've already seen before, because I'm going to loop over the same code and I'm going to reappend them. And it might be a little different this time around than last time because I've got some conditionals chaining it. And I'm just going to keep flowing out this never-ending DAG of information through my thing. Right? Well, there's maybe another way to look at that, which is to say, frequently I've got the graph in my code, and what does it mean when I say, well, under these conditions, I got something else going on? Well, a lot of times what it means is I have one relationship in my code, but I have multiple ways through it. Okay? So we can take the arrows off of our graph, and now we treat our functions, right, not as being directed things, right, but being things that we could flow through potentially if the function's invertible in multiple different ways. Okay? So we can do that by providing a package of functions for each node instead of just one function. Right? So if we wanted to represent multiplication in here, we could do 3 small little bits of code in our relationship, and then we could flow through it. Okay? How the flow is determined by something called a value or cell priority, right? So as the system's changing, you get new input. That input sets a value. Now that value, once you want to propagate that out through your system. Its priority gets raised, it flows through. Okay? So we can have something like this, okay, where we set a source value here and we set a source value there, and it flowed through to the 2 sync values. Okay? So that's what I mean by property models, and this is something that I've been working on, myself for like a decade and collaborating with Jaakko Järve on it, and we have several papers on it in a couple libraries if anybody's interested. There's some interesting stuff you can do with this. So now what happens when you start to run these things asynchronously gets interesting. You end up flowing futures through your graph, right? Because this is one graph that's been changing over time. We started at the top. That was the first graph we just saw with our 2 sources. We had flown out to 2 syncs. Okay? And then some more information came in and set our middle value. And so that reflowed our graph out. So now we've got 2 syncs on that side, 1 sync here. Okay? And this value right here that needs to be calculated to do that value, but that value is this value, which we haven't calculated yet. Okay? And that sync over there we no longer need, so we can drop the future on that. People kind of follow that? Right? So you can start to think about your application, instead of you unrolling it into this chain, okay, it becomes something where you keep shifting it in place, right? Okay, perhaps representing some such systems as if they were imperative code isn't the right way to think about it, right? Maybe at the end of the day, the way we write code with futures and with packaged tasks, right? It's this very approachable model of saying, well, we're going to write code that looks imperative, and instead of getting our integer back, we're going to get our token for an integer. But under the hood, we're really constructing a dependency graph. Maybe we should start coding by just writing the dependency graph, right? So those are the links. That's the link to the future library that I kind of mocked up to explore there. And papers and presentations, you can find these slides, the code that's in these slides. It's all runnable. Okay. Other presentations I've given are up there. Links to videos. And that's it. So I still have lots of time. So you guys are good.
Can we go back and do the task queue?
Anybody want to go back and do the task queue? Okay. Okay. So I wanted a portable reference implementation for C++ 14 of task queues, and I started on this because of bringing the system that I brought up on top of, well, first on top of Google's Pinnacle. Okay, so I have threads there in Posix, but I don't have Apple's GCD, and Apple's GCD has wonderful dependencies on libkern, and I don't have a libkern. Maybe I could have gotten TBB to run on there, but our code was mostly written in terms of libdispatch constructs, so that would have been a pretty major overhaul. HPX, sorry guys, didn't take a look at it. Okay, so yeah, so maybe under Pinnacle, but then not under mscriptum. Okay, so there's a little reference there in the corner, which on this you can't see, but that little link on the corner there is a link to a document on Oracle's website. I forget the actual name of it, but it's something like, how to do concurrent programming. Okay, and in there they have code that creates a tasking system like this. Okay, where we have one queue that we feed tasks into, and then a little scheduler that fans it out to all of our threads. We create one thread per core, and that's what they do. They give the example code on it. And I kind of cringe because I really don't want to know how many servers and how many times people have copied that code. Okay, it's in a good document, but it's not good code. Okay, but we could write it. So their code is like, I don't know, 50 pages or something. It's this monstrosity, but we can write it pretty quick here, right? So we're just going to have a queue which takes which holds functions and voids. Those are going to be our tasks. A mutex, a condition variable. It says when we're ready. We're going to have a pop function. Okay, this is on our queue. Right, this is a notification queue. Okay, so we've got a pop function, so we can pop something off the queue. We got a push function, so we can push something on. Every time we push something on, it notifies anybody who's waiting on this thing. And so you can see our pop, right, will sit waiting on our condition variable until it has something to go with. Okay, so as a task system, we can do this. We're going to grab a count of how much hardware concurrency we have, a vector of threads. Okay. Could probably do that as an array of threads. Couldn't, well, no, because it's not a compile time constant for hardware concurrency. So a vector of threads. Our run function here, right? So this is what we're going to put on each of our threads. Our run function is just going to spin and try to pop a function out and then call the function, right? Pop a function out of our queue and call it. Okay. So there we're going to construct our task system there. So we just put our run function on each of the threads as we create them. Okay. When we need to destruct, we need to join. Okay. If anybody's paying attention here, we don't have any way to exit our run function, so that's never going to happen, but we'll fix it. And then we're going to have an async function here so that we can push a function into our queue. Okay. So now we need to fix up that problem before. So we're going to add a little flag that says when we're done. We're going to add a call that says we would like to be done. Okay. Our pop function now is going to return a bool. It says whether we're done or not. That's about it. Okay. So we built it. Yeah?
Can you go back one slide? Does the ready for wait unlock and lock the lock?
Does a condition variable? Yes. Yes. Wait unlocks the lock on condition variables. Okay. Okay, so let's run it. We got a speedometer in the corner. Yeah, it pretty sucks. Okay. So why does it suck? It's not bad code. It's exactly this construct though. Okay, we just spun up 8 threads banging on one queue. And we're doing that. And it sucks. Okay. So here's something else we could do. What if we created a queue per thread? Okay. We could do that, not that hard. We're going to create a vector of notification queues. Okay. So our run now is going to take an index into which queue this run is pulling from, and it's going to try to pop off its own queue. Okay. So when we destruct now, we need to get rid of we need to tell all of our queues that they're done and then rejoin. So that was it. What do you guys think? Better?
Still have one.
Yeah, we got a bottleneck up there, right? Got a few things going on here. Okay. So here's how we're going to fix that. Okay. So when people talk about task stealing systems, this is what they mean. I've got a queue per thread, okay, and if my queue goes dry, I would like to just be able to reach over and grab something out of somebody else's queue, okay, and keep going, right? So that will do a few things. It will help the system rebalance. It will also reduce contention. So how are we going to do that? Well, let's take our function here. This was our pop function, but now we're going to call it try pop, okay? Because it's going to just try to get something out. Maybe it can't get it, and it'll return a bool whether or not it got it. Okay? It's no longer waiting on our try pop there. Okay? So if we can't get the lock on the mutex, just return false. Okay? We can do the same thing on push, right? If we can't get a lock, trying to push it, oh well, don't push it. Okay? Then we just change our run loop, okay? And we say, oh, well, we'll start with whatever one is our queue, and we'll try to pop, and if we don't get anything, we'll run once around the loop, and then we'll do a regular pop and wait, okay? And you could tune that. It could be, on 2 cores, once around probably isn't enough. Maybe you want to spin 4 times around, right? Okay. We can do the same thing on push here. Push usually has less contention than pop. But if we want to push something into a queue, we might happen to hit it at the same time somebody else is popping something out of that queue. Okay? And so it's locked. So we can't put it in, right? So now it's not that, in the try pop, it could be that it's busy or empty, right? Busy because somebody else is trying to put something into it, or another task is stealing from it at the moment. Okay? But at the same time, we could be trying to put something in and just happen to hit it at a bad time, right? So that locks under contention, right? Right? Falling into a wait case in that can be pretty painful. So we just spin over to another one, right? And in fact, you really don't even need this push, right? This could just be keep spinning until you get it, because you will, right? So it could just be the equivalent of a little spin lock there. Okay, so that's a task stealing system, just a few lines of code. I benchmarked this against Apple's GCD and Windows thread pools, and was within a few percentage, right? And if I turned my little dials up and down, some cases I could beat them, but it was kind of cheating, right? In general, I'd say within 10%, right? So, and this is just really simple code, right? And it's nice, it's C++14, it's super portable, I can bring it up anywhere, right? And now I have a decent tasking system. So, there you go. So, can be improved. There's other things that you could do if you were trying to turn this into a full thing, which is you put timers on how long a task is executing. So if you have one thread that gets stuck for a long time, you can go wake up and spin up another thread, right? So I don't bother to do that because I already have to scale down to one thread. So if that's going on, I've got an issue anyways. And that brought us back into the talk. So what do you guys think? Questions? Like, no controversy this year.
So it's very interesting. And you had to port a code base to that, this new system, or
Yeah.
to make it work,
Yeah, so
scripted basically.
right. So we've got a large code base. Repeating the question here. So the question was, so I had to port this whole big system into the browser. Yes. But it's not as bad as you would think. The code already runs on Mac, Windows, Windows 8, iOS, Android, and Linux. So, the platform dependencies are pretty thin and pretty small. This was, building a tasking system was actually one of the biggest holes in there. And then there were places in the code base that required concurrency. So, you would have producer-consumer models doing I/O, things like that. So I had to hand bust those effectively into code routines. So you just do task chaining. Okay, so instead of being producer-consumer, they just become ping-ponging tasks that keep chaining on the queue. Surprisingly, though, there were only a couple places where I needed to do that, and they're really easy to find because if you do like the equivalent of a .get, I just deadlocked and it was like, oh yeah, right there. Let's go fix that. Here we go.
Do you run on GPUs?
The engine does run on GPUs, not here. WebGL is ES 2.0, is ES 2.0. The engine kind of limps under ES 3.0. But if you Lightroom on the desktop, will light up your desktop GPUs and supports full OpenGL and a broad range of GPUs. The code here is not taking that path. It's not even taking the SIMD optimized path. We have a reference implementation of all the image processing that's just written in straight C++ code for clarity that we use to validate all of the other versions of the code. And so this is just running the reference implementations. doing that. Question here.
So, I need to cross-reference it a little bit. So the continuations from the futures
Uh-huh.
graph here, are those modeled as tasks in the thread pool, or is it that whole
Right.
graph of continuations?
Right. So the question was continuations when you have a dot then, where do they execute? And in my library, what I have is each future holds a scheduler or future package task pair. It's in the shared state, holds a scheduler, which is a small function where the thing goes to. And so when you call async to get your first future, you have to hand it a scheduler. And then by default, if you just say .then and hand it a function, it will use the same scheduler. So if I started with a thread pool or Apple's GCD, then all of my subsequent .thens will get queued into that thread pool as individual tasks.
But then there's dependency between.
Right. So they'll happen in order, right? But the next one doesn't get queued until the first one completes. But when you split, you can get them going in parallel. Right, and yes, and optionally in a .then you can pass in a different scheduler. So sometimes what you want to do, there's kind of two ways to join things in this model, right? One is to use the get try, which that's useful when, like, let's say I'm processing some state for something and I already have a state in my document. The next time somebody needs that thing, I can either return the last one I had, right? Or I can do a get try and say, oh, here's a brand new one, and just replace my old one. So you kind of do it lazy on demand in that fashion. The other way to do it is you typically end up creating a future of void, and whatever your continuation there has side effects, and you queue it in your scheduler to like your main event queue in your app, and then you have something that's running on the main thread and can go muck with your UI, or impose something on a data structure that's rooted on the main thread. So those are the two basic ways you join. Another question? No? Here?
You said something about in a single-threaded environment you can get a deadlock by calling future.get.
Yes.
Which sounds obvious, but in a single-threaded environment, what would async do in the first place?
So what
if you have only one thread?
What async will do is it will say queue this thing on to, you typically have one queue, right, which is a serialized queue, your main event loop. And so you say queue this thing on there, right? And then you're not getting performance out of it, okay? But what you are getting is interactivity, right? So if you look, like the existing futures have something called like deferred processing where they'll just execute on .get. And I've had people tell me, well, if get deadlocks, just use a deferred scheduler, and then when you say .get, it will calculate it then. And I'm like, no, that's not the point. I'm trying to keep my interactivity smooth, so I'm busting my things up into little tasks and interleaving them. Right? Question from Eric.
I don't remember if it was your task scheduler, but there was a destructor that did a wait for everything.
So in this one, for the thread pool, yeah.
The thread pool, okay,
Yeah, so that usually doesn't destruct until your application is quitting and going down. And on like mobile devices and web browsers, you actually end up never quitting. So.
You said you didn't like that future blocked in its destructor.
Yes, and if I were not having one of these as a singleton in my system, then I would probably change that. So yes.
Can you back up the slide into your URLs?
Sure. There we go. Yep.
Here for laziness.
This is available on the website.
What's that?
This is available on the website.
Yeah, so the paper, well, the slide deck, all the code that's in the slides in an executable form is available off the papers and presentations. And then in this directory, I just created a start of my future library, which that was what I showed earlier.
But there's a way to get to it from the C++ Now website. I'll make that.
Oh. Yeah.
So we don't have to actually.
Yeah, so the question was, is there a way to get to it from the C++ Now website? And the answer was, somebody will make that happen. So.
Did you experiment with lock-free queues?
So for the task stealing system, I actually did. I used Boost lock-free queues and TBB lock-free queues. It made zero difference. So because every time you have a lock on the queue, there's typically like one other thing you're doing, so you end up needing to lock anyways. Could I eke out a little more? Like I looked at Apple's GCD implementation, which is just huge and convoluted and very heavily optimized and completely lock-free. And they do beat me by a little bit. So yeah, could I scrape out maybe another 10%? Maybe. Would it make my head hurt? Probably. Would I get it wrong? Always. Yep. So, but I did look at that. Question in the back here?
Yeah, I think I know your answer to this, but I noticed you talk about cancellation, and if you're not accessing the result and it hasn't started executing yet, you just throw it away. But doesn't that mean that if you're operating via side effect, like which you mentioned before, that you're essentially losing what you want to do?
Yes. So the question was, when you drop your future, if it cancels, but what your future is doing is operating off side effects, won't that cancel the side effects too? And couldn't that be bad? Yes, it does. HPX has something like called apply, was it? Yeah, which is similar to async, but it doesn't return a future. It just goes, fires and forgets. You can actually do it directly on the task scheduler, fire and forget that way too. So typically then it's like, if you don't want cancellation, don't have the future, right? Just let it go. Another question here.
So why not an alternative decision like explicit cancellation? So I have my own future, and essentially the only way to cancel is explicitly saying, I wish to cancel this because I don't trust that developers don't just forget about futures. I mean, that's the entire point, right? To, I guess, lower contention of having to track these. To say, yeah, if you want to cancel it, say .cancel.
And then block on destruction if you didn't cancel?
I mean...
Or just not cancel and let it go into the ether?
Don't cancel, because essentially the destruction of a future isn't... I mean, that could just be somebody called .then a lot, and the last step was a side effect.
Well, yes, which gets to the maybe we need an apply so that you can anchor off on the last one. I'm not a fan of the fire and forget model, right? Because if you have something that has side effects, frequently that's holding onto resources or referencing resources of some kind, hence the side effects. So typically you have a place to put that future. So.
I mean, that's not our use case at all, right? Like, imagine you've got a lot of processing, you've got to go hit like 3 different drives, send a couple of RPC messages, and then eventually grab a resource. And those are all side effecting because you're communicating outside of your system in like a big chain of events, but you don't really care. At the end of the day, it's like, sure. At the end of it, yeah, there's a bunch of side effects happening, and you could end up with a bunch of voids. But I'm just really uncomfortable with the implicit cancellation that's happening on destruction of a future.
So
really
my thought is always kind of design your system with the idea that all your functions are pure, all your types are regular, okay? And start with that assumption and then adjust your design to accommodate other use cases, but don't bastardize that initial design, right? So I think doing something like having a dot apply that you could put at the end, which would not return a future, and let you have something then go on with side effects would be a better answer than putting explicit cancellation on futures, because if those functions are pure, you really don't care about the results. And when you're doing threading, having pure functions is of high value, because that means there's less contention, there's less blocking going on, because you have no shared state going on between those things. So that's kind of my take on it. Another question back here?
Yeah, so I tend to agree with you in terms of the design, how you assume things are pure. I guess my only problem with that is you can't, I think assuming that things are pure based on some arbitrary function that's passed is kind of the incorrect default, because you can think of a pure function almost as a subset of a function that's not potentially pure. You kind of get what I'm saying? So it seems like the proper way to handle it would be to, if your function is pure, state that it's pure when you apply that, when you call that thing. That would be the safer default.
Right, so the comment was maybe you should default to assume not pure and then have some way to specify it is pure. I think that leads to stuff that just clutters the code, right? The whole thing, like why you get, in the current design, why you get futures passed into your continuations is because that way you can do error handling. Well, I think we can do a better way to do error handling, which I mentioned earlier, and I don't think you want to design around the exceptional case, right? So it's very much my opinion that it's like for the person who wants to write clean code, let it be clean code. Now, like when I bumped into Eric at lunch, he's like, okay, well, so you can move something all the way through, but can you work with a move-only type? And I couldn't at lunch, can now. And the answer to it is if you create a future for a move-only type, you get a move-only future, right? Your future behaves like that type, right? And you can always just go to the scheduler and just say, execute this function on the scheduler, right? And not have a future for it at all if you're just relying on side effects. So then, it's a very nice property to be able to just hang on to those things and know that when you let them go, they're just gone. One more.
I mean, I don't disagree that it's a very nice property.
Yes.
But, the behavior, like I assume the whole point of this kind of talk is, okay, what's going to end up as the future, the future of futures for the STL? In general, in the standard library, the default behavior is the safe behavior, generally. So it just seems, I don't know, it just seems this big assumption that functions don't have side effects, I don't know.
So,
really awkward.
So the question was, is this talk about the future of the standard futures? That is up to people, probably some in this room. All I do with the standards committee is throw hand grenades at it. I don't attend standard committee meetings. I am not on the standards committee. I am not a member. As for the standard going overboard on trying to be safe, there is always contention between safety and efficiency, and you cannot have both. And the standard in many areas, I think, by trying to make things safer, just creates bigger and bigger problems, right? Having futures that lock or .get locks. So having this, the whole design, the whole idea of futures largely comes out of the effort for Silk, which is CILK, out of MIT. And one of the nice properties of Silk was that you cannot deadlock a Silk system, right? And they had no weights, right? So So I think it's really bad to start with the assumption and say, let's build a system where you can deadlock and you can have side effects and move only types. It's like if you want to say, can we accommodate that without bastardizing our design, do that. But I disagree with the approach of making things safe because it just gives me a headache, right?
So, as far as history and maybe even safety goes, I mean, I think the opposite approach is what makes most sense to me because it's parallel with RAII. If something goes away, it's supposed to clean up, right?
Yes.
And the fact that it by default doesn't to me would seem like a bug.
So the comment was, he thinks that this future design where things clean up when they go away is actually more along the lines of kind of the way C++ goes, where you have RAII, and when you let go of a resource, the resource goes away. So that was the comment.
So there have been points at certain points in time, the HPX features have not blocked in the destructor before the current standard proposal, I think, the previous generation of features. I think at one point, I think the previous generation did, and we stopped doing it because it does break things. I mean, it's just,
yes.
I don't like it.
Right. So the comment is blocking in destructors does break things. Yes, blocking in destructors does break things. I know, Herb Sutter can give you a whole lecture about the problems with it. So, anytime you have a system where if you require n+1 amount of concurrency, which is what a block is, now I need two things executing simultaneously, then you can always exhaust your resources. I can run out of thread pools, I can run out of threads, right? I can just take my machine down with a model that pushes me into that situation. So it's interesting that to scale big, one of the answers is make sure you can scale small, right? So if you want to scale to 65,000 cores, you should be able to scale to run on one core. Right? Yes. The comment was he disagrees.
Are you planning to add support for canceling running tasks, like with some kind of flag or optionally can be checked?
Maybe. Inside of our library for the image processing, we have a mechanism for doing cancellation. I try to avoid it. If you think about, in order to get good interactivity, when I scale down to one thread, that means I'm doing task chaining, and those tasks need to be small granularity. So if I have something that's long running, I basically need to break it up into effectively a coroutine that keeps stepping out. And I can then I've got a breakpoint. I can cancel at any step along the way, right? I just have a future to the end result, and it keeps marching down before it satisfies it. So when I let go of this, it just stops wherever it was in that process. So I don't really need the fine granularity, pull some flag to see if I should, throw an exception and back out of here type of thing. There are models like that. Like if you look at PPL from Microsoft, they have a cancellation system. With tasking system, it gets pretty hairy because one task typically fans out into a number of other tasks that feed into that, and your cancellation needs to follow the paths of those. And so this model works quite well as far as following the paths without adding too much complexity. Anything else? Okay, so I'm around for the rest of the day. Heading out tomorrow morning, but